So what I'm going to tell everyone about today, or what I'm going to talk about, is solving partial differential equations in Julia. And so partial differential equations isn't really something that everyone knows about, so I'm going to start all the way at the beginning. And really what I'm trying to do, so someone said yesterday that you're trying to recruit contributors. Yes, I always am. But what this talk is going to be about is how a whole large part of the package ecosystem is really what needs to be used in order to solve a partial differential equation. So I'm going to be going through what the process is like and what a lot of the different packages that are involved and how the Julia ecosystem is evolving to be something that can solve partial differential equations in a way that is performant and flexible. So the goal of this workshop is to not tell you like, oh, here's a function that you call and then you'll solve a partial differential equation, right? What I'm going to do is I'm going to teach you to fish, right? You know, the old saying, if you teach a man to fish, they'll be able to solve their own partial differential equation. So we're not going to talk about these pre-built PDE solvers, kind of because we don't, I'll be honest, we don't have them yet. But what we're going to talk about is how do people build things to be able to solve PDEs, and how do you as academic researchers or people in industry, how can you make use of these tools which are in Julia to solve the problems that you need to solve? Or if you're just kind of here because you're curious about PDEs, I'll also teach you about what is a PDE and how do you discretize it, and what do people who are interested in PDEs, what do they care about? So first of all, what is a PDE? So a partial differential equation, I just call it PDE all the time. It is a differential equation with partial derivatives. It's differential equation with partial in front. And so what does that really mean? So a differential equation is an equation that says how something changes, right? So you say that u prime equals some function. And so I say, hey everyone, if how everything is changing is like this, where will I be in 5 minutes? Ooh, if you know my velocity, you know where I'm going to be. But it's a math problem that you actually have to solve to find out, going from ideas of change, how do you get to the ideas of position? So a differential equation is an equation that's based on change. And now, if you have only one direction, then you can say, okay, how am I changing in time? That's your standard differential equation. Now, what if I say I have something that's changing in time and space, right? So I have, let's say the temperature in this room, right? Near every single person, there's a higher temperature, and that kind of diffuses out. And I want to say, how does the temperature in this room change over time? So in order for me to talk about temperature of this room, I need to say, the XY position right here, or XYZ position over there. What is the temperature in that spot of the room? So what I want to be able to say is, how does that function of temperature, that XYZ function, how does that evolve over time? And that is now a partial differential equation, right? Because you have things changing as you go along x, as you go along y, as you go along z, and as you go along time. And so this equation will tell you how things are changing in each direction, and what your goal is to find out what is the actual temperature in the future at each point in space. So who's interested in PDEs? Well, pretty much anyone, because if you got anything that has multiple directions, multiple things involved, then if you want to find out what's actually going on, if you only know how it's changing, then a partial differential equation solver is how you're going to get that solution. So how do you represent a PDE as a mathematical problem, right? This might be the first walkthrough that you'll have of a PDE solver. If it's not, well, then sit through it. So what is the best way to solve a PDE? So PDEs are a hard problem. So what do you do with any hard problem? You change it into a problem that you already know how to solve, right? So a PDE, the way that you usually solve it, you say, I have this equation, and I want to change it into something that's a linear system, so either an AX equals B problem, solve for x, or you can change it into a nonlinear system, which is a g of x, some nonlinear function, equals 0, find x such that that equals 0, or some ODE, right? So if you know about ordinary differential equations, that says, u prime, the change in u goes by this function. Find the u that satisfies that it always changes like that. So a PDE is this equation which has multiple variables in all these different directions and all these different derivatives. But in the end, if you massage it correctly, what you get is either a linear system, a nonlinear system, or an ODE. And those are things that you can solve. And so I know that some experts in this room are going to say, oh, there's a whole bunch of other things that you can do, right? So you can turn it into an SDE, so there's other methods. I'm not going to go into those other methods. I'm going to say this is pretty much the standard way that you handle 95% of PDEs. So let's look at how that's actually done. Right? So let's learn by example. Everyone loves examples. So this is what's called the Poisson equation. That triangle right there, what it really just means is the second derivative. Right? So I'm using a little shorthand here that says u sub x is just the partial derivative of u by the partial derivative of x. So you have this function, u of x, and you say that the second derivative of your function equals some known data, b. So if you know the second derivative of your function, recover what your function must be. In this case, you can actually just solve by some integrals, but this is where we're going to establish how you can solve these kinds of problems in general. So the first choice is your computational representation of your function. We have this function, and we want to say, okay, how do we put this function into a computer? And what we can say is we can go, well, we can have this x sub I be I times delta x. Right, so we have 0, then you have delta x, 2 delta x, 3 delta x, and you can say at each one of those points, I remember what the value of the function is. And let's say we just put a line in between there. So it looks kind of like this. So you have this real function, this blue function, and then what I say is that I'm representing this function in the computer. I can't do something continuous. So instead what I do is I say, I put these points delta x apart, and I store the value of u. So now I have my function is now represented by just a vector of numbers. So I have u here, u1, u2, u3, u4, dot, 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 dot. And I can recreate my function, right? I can say if I know what my delta x was and I know what my u was, I can put a line between them. And if you have enough points in there, you'll be close enough to representing your function well enough. So now I have a way to be able to say, this is a representation of my function. I can't put a continuous function in a computer, but I can say that this array of values represents a function close enough. And now if I can represent a function like this, how can I discretize my PDE such that my derivative operators are written in the same language as my discretization of the function? So I can say, well, my function just has these points in space, right? So I know what my u values are at these different delta x's. And so what I can do is I can say that the forward derivative, right, the first derivative can just be the point in front minus the current point divided by delta x, right? You take this point here, you take this point here, you subtract them, you divide by delta x, and that gives you the slope in the middle. That's just your very basic derivative approximation. And again, if this function representation is good enough, if my delta x is small enough, then that will give me a good enough approximation of the derivative. And then you can do the same thing with a backwards difference. So how do you do a second derivative? Well, the second derivative is just the derivative of two derivatives, right? So since we have a forward derivative and a backward derivative, what we can do is we can say, take the difference between these two different representations of the derivative, divide by delta x, and you get this formula which says, here's one way to be able to represent what a second derivative is if you've written your function in this form. Right? That conditional right there is one I want to really keep track of. I say, this is the second derivative if I've represented my function as points evenly spaced on that line. So a quick recap, we did make two choices, right? So first we represented our function by a grid of points, and then we chose a representation for our derivative. There's a bunch of different ways where you could say, a second derivative is defined by this, this, and this, and you come up with a different discretization. But here's just one choice that we made. So given these two choices, how can we rewrite our PDE equation such that we get something that's computationally representable and we can solve that? So the representation of our PDE, this is the part where I want to slow down a little bit. So we want to solve that the second derivative of u equals this function b, which is known. And so now we have this grid. We say that we can take points at every delta x. And so instead of having u of x, let's take u sub I, this vector of u values, which is the values of u at these grid points. And now this data function that I have, let's just say I also want to get a vector of these. So now, we're all computer people, right? So instead of thinking about it as mathematics, now just think about it as I gave you a function, and you say, well, I don't know how to actually hold this true function. I don't know how to actually do mathematics on a continuous function. So let's just evaluate it. This is you broadcast it, right? You do b dot of x, where that x is that linspace object, so that way you get out all your different values. So now we have a vector of values u, a vector of values b. And what is our second derivative? Well, our second derivative is a function, a very simple function on our vector, right? So if you have this vector of points and you say, what is the second derivative at the I spot? You do the I minus 1 minus 2 times the I, and then you do the I plus 1th one. You add those together, you divide by delta x squared, and that is equal to your derivative, or your second derivative. And now if your equation is, well, the second derivative has to equal b, just write that down. Here's my second derivative equation, written out in terms of the vector. Here's what it's supposed to equal, written out in terms of the vector. And now this is something where you can kind of think about it as a loop, right? For I in each 1 through the length of the vector, these things have to be true. Solve this equation, or find the u vector such that the u vector satisfies that it has to equal to b on this side. So now our equation has become something, it's gone from something that is continuous to now this is something computational. We have a loop where we know what these values are, and when we loop through on this side, all these things got to be true. What's the u that solves that? But wait, all right, so there was one thing that I kind of skipped over that I know that some people were thinking about, and it's that what happens at I equals 0, right? So let's just think about this computationally. So at I equals 0, you put in the numbers, you have u sub I minus 2u sub 0 plus u sub I minus 1. Well, that should be just minus 1, right? And so if you put at inbounds in front of your thing, you will segfault Julia because you are indexing off of your array, right? You can't go to the minus 1th point in your vector. So what happens at the edge? Well, the PDE is not well defined without a boundary condition. So you have to say the temperature in this room, let's just say we have this heater over here. If the heater or the air conditioning, if that's always at 73 degrees Fahrenheit, Fahrenheit's the better way of saying temperature. So if it's always at 73 degrees Fahrenheit right here, then we just keep that constant, right? So it'd be like saying, this value right here, the u sub minus 1, when you get off the vector, we just assume that that's always some constant value. And if you've assumed that it's some constant, then you can solve your equation because you can say, oh, let's just put in that constant value, and we know what it is. So there's a few different ways to be able to give boundary conditions. So you can say things like, the derivative at the interface is 0. That means that every single molecule that would be going over the boundary, it bounces right back. The heat doesn't leave the room. So you can have different ways of describing a boundary condition. But here let's just say the easiest one, which is we keep the boundary constant. So the heat at the edge of the room is always going to be 0 in our case. It's a very, I've scaled temperature to be something different. So when we take this equation, we say that I should have moved it over by 1, but u sub delta x minus 2 u sub 0. And then when we fall off, we just say, well, those are all 0 because of how I define the boundary condition. I should have actually written this as 2 delta x, and 0. And then, yeah, but whatever. So, okay. Oh, that's actually what I do down here. So yeah, at the bottom I say, you know what, if we just say that at the endpoints we already know what it is, then we can say that this value is 0. If I just say that this is going to be 0, then I can take it away. And now what you can see is that your system is okay, right? At I equals 1, you no longer have any values hanging off on the end. At I equals at the very end, then you don't have any values at the end. So your nice little for loop here is very closed off because there's no value hanging off on either side. And now you can say, this is a loop only over values in my vector, and it's well defined. So we can solve it, right? How would you solve this equation? Well, let's represent it a different way. So you were thinking about it as a loop, but now let's think about it as a matrix multiplication. So this is the language where everyone should understand. Everyone, even in machine learning, you guys are still doing matrix multiplications. We're all doing matrix multiplications everywhere, right? But this is now kind of an abstract one. So here what I'm saying is this 1 minus 2, 1, what that's saying is that u of 1 minus u of 2, 2u of 2, plus u of 3 divided by delta x. Well, if you go back here, you'd see that that's exactly this equation. Then what it should equal is that b sub I. Right, so u sub 1 minus 2u sub 2 plus u sub 3 should equal b sub 2. And so that's exactly what this matrix multiplication is saying. Right, so if you actually run through this matrix multiplication, you see that this is what you get out, and this is what our loop was, where you say that this value equals this value equals this value, and on the endpoints, what you see is that we made those u sub zeros equal to 0 because we assumed that on the boundaries we're all 0. So the nice thing about this, though, is that now this is a matrix, this is a vector we want to find, and then this is a vector of numbers that we know. Does anyone know of a nice way in Julia to solve that equation? Well, I'm not going to tell you quite yet. So let's actually do this on a real equation, right? So we want to find the second derivative equals sine of 2 pi x. What is the function that gives us that? So what we're going to do first is we're going to build our matrix, right? So what I said was you have this nice matrix where you have -2's along the diagonal, and then you have your 1's on the off diagonals. And the reason why these are 200 and 100 is because, remember, we have to divide by delta x. So it's always going to be the same matrix, but scaled by whatever your delta x was, or delta x squared. So the way that we solve this in the end is backslash, right? We want to find the u such that a times u equals b. Remember that the way that you solve that linear system in Julia is backslash. So what this was really doing is we've really, in the end, I just said, oh, here's all this mathematics, but really what it comes down to is the computational problem in the end is a linear solve, which you use backslash. And here we get the solution out. The question is, did we actually do that right? So, right, I mean, this is a simple calculus problem. What's the function that gives you, the second derivative is sine? Well, it's going to be the negative sign, right? And so if you actually check the analytical solution, if you want to go over my slides, you'll see that, yeah, I'm right here. But the nice thing is that blue line, right, that blue line did not use anything about calculus, really, other than the fact that, well, it had it embedded in how we came up with discretization. But the whole idea of what we actually did was we said, where was it? We had that this matrix times this u equals this b. We know this b, find this u. And so what we do there is we did backslash on this matrix right here. Right? So that's what a PDE solve is. If you can get to this representation where you say, here is my derivatives written like this, so now I have a matrix and I have a vector, then I do a matrix vector solve, and you're done. So solving a PDE is not about trying to work with the PDE as much as it is trying to get it to a different problem that you already know how to solve. So let me recap that a little bit. So we solved the PDE, which was the Laplacian of u equals b. And what we did was we transformed our continuous functions into vectors. Right? So we chose some way to discretize our function. We said, hey, using points, using evenly spaced points is a nice way to do it. If we take evenly spaced points, then we can define our derivatives in a way that makes sense on our grid. And if we have a way of defining our derivatives, we can rewrite our PDE equation to be in terms of this vector. And now that we have everything in terms of a matrix times a vector, now we just have to do some linear algebra to be able to solve that problem. And so one thing that comes out of this I do want to point out is that since derivatives are linear, it always tends to happen that pretty much any way that you choose to discretize these things, you will get a matrix out for your PDE. So I'm going to go over in a sec all the different ways that you can discretize. But the idea is that you take this equation and you choose some way to represent your functions. And when you do that, all of your PDE operators, all your derivative operators will become matrices. And then you just have something that's just vectors and matrices solve for the vectors. Or you have something which can become an ODE. But so the entire idea is you want to get something to linear equations which are linear or somewhat have some nonlinearities that you know how to handle. So what are some other PDEs that we could look at? So you said, oh, maybe I gave you the simplest one. Yes, I did give you the simplest equation to start with. But what's a more difficult PDE? So the semilinear Poisson equation is now we say that the Laplacian of u equals f of u. So now this right-hand side depends on u. Right? And so we say that we know what this function is, but I can't tell you what this, you can't give this, I can't give you that as a vector until I know what u is. So let's say we ran the entire process again, right? If we ran the entire process again, we discretize our u, we come up with our derivative, we use the same matrix for the derivative. What we get in this case is we say that our second derivative, right, which is represented as this matrix times the vector, equals this nonlinear function of that vector. So I can take, this nonlinear function is just, you put in a value and it spits out what the value should be. It's just a value transform. This is now a nonlinear function where it's applied broadcast-wise to a vector, right? So we're all Julia users, you put the dot in right here. So now you want to find the u that satisfies this matrix times vector equals nonlinear function of vector. What would you do? Well, let me rewrite this a little bit. And then you say that this is some g of u. Let's define g of u to be f of u minus au. And so what is the solution to au equals f? That's the same thing as saying g of u equals 0. Right? I just took this side, I subtracted over here, and defined the whole equation to be g of u. That's all it was. So now, instead of actually solving a problem which is a PDE, now we say that all we need to do to solve this problem, this semi-linear PDE, is we need to find the u such that g of u equals 0. And so this is a root finding problem. This is one of those classic root finding problems that you'd use Newton's method to be able to find what is the zeros of that equation. So once again, we didn't have to, solving a PDE was transforming it into another problem that's already been solved. So let's look at another case, the semi-linear heat equation. So now we have that u sub t equals u sub xx plus f, where this is some nonlinear function. So this is actually a better representation of the heat problem, right? So now what we can say is that u is the heat over x, where I'm just looking at x is where I am or this direction in the room, and t is time. And I say that this term is saying how heat diffuses, and this term is some nonlinear thing. And I say, how is the heat changing over time at every single spot in space? So let's run our same exact thing again, right? So we say, let's represent our function in space by the points, delta x apart. And if we do that, then we say, well, what's the second derivative if we've represented a function like this? You get that same matrix. And so once again, our second derivative can become this a times u. Our nonlinear function is now f of u, and then it can also have time. And now I didn't do anything with this t. But if you look at this equation, and you say, well, I might recognize this before. I only have one type of derivative, so I can rewrite this differently. I can say that this is u prime equals something over here. And now this is just an ODE, right? So you take differentialequations.jl, and you plug it in there, and it gives you out an answer. And what that answer is it tells you what u should be at each of these points in space over time. So what you basically get out is that you can keep on changing these derivatives into matrices, and you can leave some undiscretized, and then you end up getting a different differential equation with less things that are derivatives, but those end up being ODEs. So you can either solve the ODE, or you can once again say, well, let me discretize this in another way, right? You can choose another way to discretize, and you either get a linear solved problem or a nonlinear solved problem. But in general, you get these three types of problems, right? You get the linear solved, the nonlinear solved, or an ODE out of your way of discretizing. And now you might have to ask the question of, well, okay, I've only been talking about low-dimensional equations, right? If you want to do a three-dimensional equation, how is this different? And the answer is it's really no different. Because let's say we have a two-dimensional equation, so u sub xx plus u sub yy now equals a function of x and y. What I now have to do is I now say, let's let u be the entire vector, right? So I have, I grid it so that way I'm going across the square. I go u sub 1, 1, u sub 2, 1, u sub 3, 1. You go across, and then you go down 1, right? And so you can say, here's my whole square. I took the square and I called vec on it. So now I just get the vector instead of it as a square. But it's just a different way of writing out that square as just a vector. And now how do I write out my second derivative? If you run that same process again, what happens is you just say, well, the point in front minus the point minus 2 points in the middle plus the point in back, that's the second derivative in x. And then I can do that in y as well. And so that's now a new matrix on this bigger vector. And as long as you can convert, the indexing gets a little bit harder because you need to be able to say that the point that is one behind in the y direction is going to be actually n apart because you have to walk through all of the horizontal part first. So the indexing is a little bit more difficult. But in the end, you just have another matrix. You just have these values times a matrix which has 1s and 2s in it, times your big U vector. And what do you have to solve in the end? Well, now you have your B written out in the same indexing, and you solve AU equals B, and you once again just use backslash on that. So it doesn't really matter whether you have multiple dimensions, whether you have multiple derivatives. In the end, solving a PDE is all about discretizing a function, and then once you choose a discretization of your function, you choose a discretization of your derivative, and once you have both of those, you get a new problem, which you can represent on your computer as a linear solve, a nonlinear solve, or an ODE. And so really what it comes down, what building a PDE ecosystem is about is not so much talking about PDEs, but a lot of it is actually just talking about how do you solve the linear equations, the nonlinear equations, and the ODEs that come out of these discretizations. So part 1 summary, to solve a PDE, you choose a way to represent your function, you choose a way to represent your derivative, and you get either linear system, nonlinear system, or an ODE. I hope we're all pretty clear on that now. For some of you, that's probably review. For others of you, that is, you've now solved your first PDEs. And I've walked over it really quickly, but now you guys can all get your PhD in math. So you just walk in there and say, I know how to do everything with PDE. So is it that easy, right? So I said, we chose a way to discretize. Well, are there different ways to discretize your function? And the answer is yes. There's pretty much, if you go to any applied math department anywhere in the world, you'll find, half the department has their own way to be able to discretize a PDE. This is what a lot of people are researching. And so at each stage of this process, you actually have a different set of packages which are all helping the PDE solving ecosystem. So you have everyone has their own way to be able to represent these functions as vectors. You have all these different ways to be able to solve the linear systems that come out. You have all the different ways to be able to solve the nonlinear root finding problems. And then you have all the different ways to be able to solve ODE. And it's really these 4 types of things together, that is all what we can call the PDE solving ecosystem. So it's not one package, it's not even one organization. This is multiple organizations and hundreds of contributors across Julia that it actually takes to be able to solve these PDEs. So packages that represent functions and derivatives. There's quite a lot of them. But a lot of them are still developing. So I'm going to go over DiffyQ operators because this is one that we have in Julia DiffyQ, and it's heading in an interesting direction. I don't really know of one for finite volume methods. So the finite volume method is just one different way of being able to discretize, where instead of looking at points, what you do is you look at the integrals of small areas, and then you see how if you can represent the integrals of small areas, how do the derivatives of those change? Finite element methods, I'm going to go over that in more detail. There's multiple packages in Julia, and a lot of people are building different ways to be able to do the finite element methods. And then spectral methods, I'm going to be talking about FFTW, so how can you Fourier transform solve a PDE, and a proxfun. So if you don't know what a proxfun is, it's right in there in the name. It approximates functions. So the finite difference method, we have DiffyQ operators such al. What exactly is it doing? Well, it's doing that process which I just described to you. So you say, well, I didn't talk much about the order. So when you do this discretization, you have how fast does it converge? That's the order of the derivative. And so the one I was talking about, that 3-point stencil, that was a second order approximation to the second order derivative. And so what this package does is you say, I want the second order, second derivative, and my delta x is 0.1. And so I say, I want the derivative operator that does that with these boundary conditions. And then it gives you this A. But notice it doesn't actually give you back an array. What it gives you back is this lazy object, right? So it's an object that has star and A mole B, well now mole defined, such that when you multiply it by this, it acts like it was that matrix that I told you about. So it doesn't actually take up any more memory than holding these values, because on demand it knows how to build the function that is the matrix multiplication without the matrix actually existing. And so just as an example, you can say, what is the fourth derivative, right? So what is the discretization of this to a second order when I have delta x equals 0.1? Then here I build the operator, and that's a lazy operator, remember, but if I want to actually look at it, you can call full on it. So full, remember, it gives you the matrix. And so now this is what the matrix is for that fourth derivative. So if you wanted to solve the fourth derivative of u equals b, then you'd say, oh, just give me that operator. This is that matrix I now need to use, and use backslash on it. So this library, what it does is it uses something called the Thornburg method, so that way it can just automatically know what the discretization matrix has to be for different orders and different derivatives. And also what we're building it towards is so that way you can use not just a single delta x, but you can give it a vector of delta x's, so that way your points don't have to be evenly spaced. So we're building that in that direction if you want to be able to use finite derivative or finite difference methods, and it's coming out pretty nice. But we will need, I'm not going to say it's actually out. It's not in the DiffEq docs yet because we're still working on it. And if anyone's interested, it's a great GSOC project to work on next year. So yeah. So a brief overview of finite element methods, right? So finite difference methods, those are the methods where you represent your function by points, and DiffEq operators is one package to be able to help you build the matrices from that discretization. Because remember, the whole point is you can easily get the vector that is the points of your function. The hard thing to get is that matrix, but once you have the matrix and the vector, now you have a problem that you know how to solve. But you don't have to do your function via points. You can also talk about it as, here's my function, and it is the sum of some basis elements times coefficients. So if I told you what the basis was, and I told you the coefficients, then you'd be able to recover what I'm saying the function is. So what the finite element method is the choice of element is a choice of basis. So then what you actually need to hold on to, what your vector actually is, are these c sub i's. And then it tells you how much you need to add together each of your bases such that you rebuild your function. Now I can talk about it all I want, but you probably won't understand it until I show you a picture. So here we can say my bases are these little triangles, right? These little, we call them hat functions. So here's the first element, here's the second, here's the first basis function, here's the second basis function, phi1 and phi2. And now my question is, how do I represent a function u in terms of this basis such that I can add together these functions in a way that approximates the original continuous function? So let's say we had it instead for a whole domain where we had 9 of these basis functions. What you can see is that if you take the function at this point, then that would be, if you say that you have c sub I times this x sub I, then this triangle plus the next triangle is going to give you a function which has exactly this point. So if you actually take these hat functions, you actually recover the other method where you say, well, I can store the point values. But this is something else that's a little bit more general, right? But the basic idea is that you can take these little functions, and if you add them all together, then if you know how to be able to translate, then you can say my coefficient values times my function. If you add them all together, you get a nice function over your whole thing. And if you have enough triangles in there, then you'll be able to approximate this well enough. So I kind of went hand wavy over that, and I said in some cases it's easy to get the coefficients, some cases it's not. That's where the real mathematics comes in, right? So if I give you some arbitrary curve, and I say, well, find the way to be able to add together these functions such that you equal this, you approximate the function I gave you, well, that's not an easy problem to solve, and that's why you have a package that does it for you. So the nice thing about finite elements is because it goes to, the nice thing about finite elements is that it easily goes to domains which are not easily described by squares, right? So when I said that we had these grid of points and I did the finite difference method, I basically assumed that we can either take, we had some kind of a square, right? We can go evenly spaced along x, evenly spaced along y, but that's very limiting if we want to solve PDEs which are related to real physical problems. So what we can do instead with the finite element method is we can say, well, we can use two-dimensional elements, right? We just need to be able to write our vector in terms of functions that we can add together. Here's a function that's two-dimensional, and so we can represent a two-dimensional function by adding together smaller, easier two-dimensional functions. And so then we can tile pretty much anything we want. We can represent a function on this dolphin by saying, how much of this triangle plus how much of this triangle, and you add them all together, then you can represent a function on this weird domain. And this is a nice toy. This is actually taken from the Phenix examples. But this kind of sounds silly until you see that, well, we actually want to be able to represent, like what is the stress on a car, right? We want to be able to represent the values of x. We want to be able to say at this x, y, z, what is the value of stress? And we want to be able to solve that PDE. Well, then we need to be able to tile a domain, which is very, very unstructured. And the way that we're going to do that is with very small triangles or very small tetrahedrons at each of these points. Or the finite element method, right? You've probably heard that, everybody has their own finite element method, right? There's HP elements, there's so many different elements that you can find. And they're really just different ways to be able to tile these kinds of domains so that you get different properties in the matrices that come out. So every package, then what they're doing is they give you a way such that you can represent your function in terms of a vector of coefficients, just that when they're that coefficients on that basis, they're now approximating the function. And then what it also tells you is that if I've represented my function in terms of triangles on this 3D space, what's that matrix for the derivative? Well, what they've actually done is they do the mathematics in the back end, which says the derivative matrix only needs this point, this point, this point, and this point, and then they do a stencil on this weird on these coefficients. So the idea is pretty much the same. You get a vector, or you change your function into a vector, and you change all your derivatives into a matrix. In this case, the matrix is going to be much more difficult, but you still get the same pieces out. It's still pretty much the same process, just a different way of representing your function and your derivative. And so one package for doing this is phenix.jl. And this is actually a wrapper for the well-known Python package. And so this is actually maintained by the Julia DiffyQ organization. It's been developed over 2 years as 2 GSOC projects. One pro about it is that it's pretty fully featured, and it has a lot of linear solvers built in. Right? Remember that the linear solve is the key part to actually solve the PDE in the end. But the problem is that it is not fully Julia-based, and it's missing a lot of the fancy Julia features, right? Because it's actually doing PyCall. You can't just give it a vector of arb floats, or you can't give it a vector of big floats and just expect it to work, because Python won't know what to do there. But it is just, if you take right here, I think this is the first tutorial of Phenix, and then you just translate it over to Julia, where you take they put a bunch of weird dots in places. We just make it, actual function calls. And then this is your Julia code. It's almost the same as their tutorial. You now just call it in Julia, and it will build your matrix. So what you put in here, you just say, these are the functions that I want to represent. These are the boundary conditions. I want to use these types of this type of basis. And now give me the linear operator that corresponds to that discretization. Now change my initial function into that vector, and then just call solve on it. It's the same process that we did before, where you say, here's my function, turn it into a vector, build the matrix, call solve. This is exactly the same thing, except now in the language of this package, which does it using these triangles instead of in the language of using points in space. And so the nice thing about this is you can use this package to be able to handle these larger domains without having to do all of the details of that discretization yourself. Because at some point you need to abstract away from doing every little detail. So I showed you something that is a PyCall package. Your next question is going to be, well, I want something that's pure Julia. Well, what do we got, right? So Julia FEM, this is actually a whole organization which is building finite element method tools. And they're building it more towards physics-based problems. So what I've been discussing is everything from equation-based. In this literature, you can have something where you can talk about the PDEs that you're trying to solve as either, it's either the stress equation or the heat equation, or this is the PDE of the second derivative. So you can either talk about it in terms of the physics, or you can talk about it in terms of the equations. And the Julia FEM group, what they're doing is they're building in terms of the physics language. Right? They're building the physics-based finite element method discretization tools. And I don't have an example actually to show from them, but they have a lot of stuff that you can find online. I needed to cut something because this talk gets long. Another thing that you might want to look at is juafem.jl, which was this. So what this library does is it just gives you a bunch of helper routines. So it's a toolbox instead of a full end-to-end PDE solver. And what it does is you basically say, here's how I want to choose the elements such that they're the triangle. How do you build the matrix? Well, it gives you functions that helps you do the matrix assembly portion. So the building of the matrix is called the assembly. And so if you walk through the documentation, what it shows you is it shows you this function, which is do assemble. And what it's really doing is it's building your matrix and your vector from your input. So you say, here's the domain I have, here's the function that I want to discretize, and here are the derivatives that I want to find the matrix for. You put it helps you build a function that does that. So it doesn't give you the function that gives you the matrix, but what it does is it has these cell iterators and it has all of these helper functions that make it much easier to be able to do this, because really all of these matrix assembly problems, what they are is they're much smaller matrix building problems. And so those much smaller basic matrix building problems are only dependent on the type of basis functions you've chosen. And so they've hard-coded what the answer is for a lot of these basis functions. And so this helps you build a function that gives you them. So this is what I'm calling a toolbox, right? It doesn't exactly, you don't just say, here's my PDE, solve it for me. But what it does is it gives you the tools to be able to build the right thing to solve your PDE. So those are 3 different ways to do it. So Phenix is more of like a front end-to-end. You put in your equations, you put in the basis that you want to use, and it gives you, and you say solve, and it solves the PDE on it. You have Julia FEM, which is building it more from a physics standpoint, where you input what the physics of your equation is and what domain you want to solve, and it gives you out, like the stress tensors and all that. And then there is this JUA FEM, which is more about giving you the right functions such that doing the discretization by yourself is much easier. But these are all the same thing, and in the end, what you're really looking for is matrices and vectors that are for your function and your derivatives, and then solving linear equations. So spectral methods is another way of writing out these, u of x equals the sum of some constants times functions. And what you want to find out are these, right, C sub I. And really the finite element methods and spectral methods don't end up being too different, except usually you choose some global basis functions. Right, so when I talked about the basis functions for finite element method, they're all local. I said, look at these little triangles. They're 0 outside of some area. These spectral methods, they try to be global. Right, so what is one way to be able to discretize a function that is global? Well, one nice way to do that is using sine functions. Right, so if you know Fourier's theorem, then you know that sine of x plus sine of 2x plus sine of 3x plus sine of 4x, if you take that infinitely long, and then you say, well, how much of each sign do I want to add together? You can recover any periodic function. So this is another way to represent functions. If I tell you, C sub 1 is equal to 1, C sub 2 equals 2, C sub 3 equals 3, and then all the other ones are 0, then that's another way of saying that my u of x is equal to sine of x plus 2 sine of 2x plus 3 sine of 3x. And the question is, if I know a given u of x, can I find this sign representation that is good enough, right? And so what you have is a fast Fourier transform is the process of going from a continuous function, well, it's going from a point discretization of this continuous function to what the values of the c's are, such that you now have represented it in terms of sine functions. So if you've never seen this before, let's actually just do some Julia code to do this. Let's take our using fastest Fourier transform of the West. X is the Lin space from 0 to 2 pi, 100 points. And now what I say is my u of x is this sine. And now instead of actually using the continuous function, I'm just going to evaluate that continuous function at these 100 points using my broadcast. And so the fast Fourier transform of those points, if I look at them, so it actually does the forward frequencies and the back frequency. Let's just, there's a few other details in here, but the way that you would recover what the c's are from the fast Fourier transform is you take half of them, and you take the absolute value, and you'd multiply it by 2. And so so now we've represented our u of x in terms of a sum of sines, and this was sine of x. So what is our representation in terms of a sum of sines? It is, well, that's basically 0. That's basically 1. That's almost 0, and as you can see, it's almost 0. Right, so it's saying that our representation of sine of x is 0 plus sine of x plus 0 times 2 sine of x plus 0 times 3 sine of x dot dot dot. There's a little bit of discretization error, right? Because it depends on how many points we've taken. If we take more points, then these other coefficients will be closer to 0. And so there's always going to be some representation error, but that's just because we're using a fast Fourier transform. We can actually just put in the analytical solution in this case. The best way to represent a sine function would be 0, 1, 0, 0, 0. And so this gives us a nice way to be able to represent a lot of these functions. Now that it was once a sine function, now it's a vector of coefficients. Now, why is spectral discretization a nice way to do it? Well, one reason is because they converge really fast. They converge exponentially fast if your function is continuous. But another reason is because derivatives are really nice to write in this representation. So actually, let me just go to Approxfun for that. So yeah, Sheehan just looked up there. So I said that there's this kind of difficult part, right, where you had to kind of look at, you take the fast Fourier transform and then you take this half and you multiply it by 2. Well, if you didn't want to have to remember any of those rules, but you still wanted to do a spectral discretization, well, you can use this approximate functions package, Approxfun, to be able to do that. So what does the Fourier transform look like in terms of Approxfun syntax? So let's instead this time do something a little bit more difficult. Let's say r of x equals the cosine of x minus 0.1. Let's represent this in terms of that same Fourier basis. So what we do is you say my space is the Fourier basis. I want to use 100 points. You say this is my t is the forward transform. So the t transforms from the point basis back into the sine basis. And you can also say the I transform. This is the transformation backwards, where if you know what sines you are, then how do you get back to your points? I'm going to use that one in the next slide. But so you can always transform two sines, and you can always transform back from them. And now I say that this x is actually represented as these points. And what you do is you just say t, and so you apply the transformation operator to your function. So here's my function, and I apply the transformation operator t to this function, and I only transpose it so that way it prints out well. And you can see that what I get is I get a approximation in terms of the Fourier space. And Approxfun is really just what it's using in the background is a discrete Fourier transform. So it's doing the same thing, except now this is like a nice DSL kind of way of writing it, where you say, this is the space that I want to use. How do I transform to that space? How do I transform back from that space? And Approxfun gives you really nice operators for doing those. And so what is the derivative of, so what is the second derivative in terms of the Fourier space? You can actually work it out that it's this diagonal matrix. And that's the reason why a lot of people like these spectral methods, because, well, your derivatives are really easy to write down. If they're all diagonal matrices, this makes your linear solves very easy, right? But Approxfun is really nice because you don't have to just choose the sine basis. You can choose a bunch of other different bases really easily. So let's say we wanted to use the Chebyshev basis, right? So these Chebyshev polynomials they're defined like 1x, this weird polynomial, other weird polynomial. They have a recursive definition to what the polynomials are, but this is some basis that we might want to represent functions on minus 1 to 1. And the way that we would do this in Approxfun is we would say my space is now, I want to go to the Chebyshev space. Here's my forward operator, here's my backwards operator. Here, I want to go from these points, take this function, transform it to that basis. And if you notice, the code is pretty much the same. The only thing that I changed is I said, I want to use this other space. So if you go into their documentation, they have a bunch of different function spaces. And the reason why you might want to use a different function space is because, well, the Fourier space is for transforming functions which are periodic on 0 to 2 pi. This space is now for transforming functions which you define from minus 1 to 1. And so this gives you a way to be able to discretize functions which have different properties just by choosing the correct space. And if you go into their documentation, they define what all the possible spaces are and all the different approximations. And the next thing that you might want to know of is, well, if I know how to represent my function in terms of a coefficient vector, the other thing that I need to do in order to solve a PDE is I need to get that matrix, right? And how do you get that matrix? You just say, what is the derivative in this space, that second derivative, and it gives you what that matrix is. And approximation does a bunch of really nice things here too. So this is a derivative matrix, which is actually infinitely long. This is another one of those lazy operators, right? Where if you ask it what it is at the 100,000th row, it will know how to be able to generate that because it's generating it on demand lazily instead of holding the whole matrix in there. And so remember, this is just a different way to be able to discretize your function and discretize your derivatives. And then what you're able to do to be able to solve your PDE efficiently is you use these discretizations, you find the one that is best for your problem, and then you use these packages to really help you get to, here's my vector, here's my matrix, solve that linear equation, solve that nonlinear equation, or solve that ODE. So the part 2 summary is that you have all these different packages which are different ways to be able to get to vectors and matrices. And so there's actually a bunch of different ways, and people can study mathematics forever with coming up with brand new ways to be able to do this. But each one of these packages is giving you the same thing as an output, right? They're giving you either a linear equation or a nonlinear equation or an ODE using different methods to get there. And each of these different packages will work better or worse on different PDEs, right? Finite difference method is really easy to get done if you have a square matrix, if you have a square domain. A spectral method might be able to do it with less points because it's doing it with global discretization functions, and also has these nice diagonal matrices which can make the linear solves a bunch easier. Or finite element packages, they can handle these weird domains, right? You can discretize the stresses on your car. You can discretize, you have these weird cutouts on the desk here. You can say what is the stresses on this desk, and you can handle domains which are very non-square and very difficult to actually write down by using these triangles, right? But these are all different ways of being able to say, here's the thing I want to discretize, take the function on it, make it into a vector of points, make a matrix for my derivative, and now what do we do from there? And that's the rest, right? Now we have these 3 things that we need to be able to solve well. So equation solving. One thing that we do have to discuss, though, is that the reason why PDE is such an interesting topic for these 3 types of equation solving is that they have they all show something that's very similar. And so if you remember that finite difference matrix, it was a 1 minus 2, 1 on this diagonal. If you saw those, when you saw those other discretizations, right, you had the Fourier matrix, which just was diagonal. You had the Chebyshev matrix, which it was off diagonal, but it just had points on that off diagonal. What you notice is that all of these discretizations tend to be sparse. They're not all sparse, but you have a lot of these sparse matrices where if you know the discretization process, you can know exactly what your sparsity structure will be. Right, so you can get these very nice matrices out where you know it's going to be a banded matrix, it's going to be a block banded matrix, and what you need to do is now you need to be able to solve a linear solve problem on these special types of matrices. And so what happens is that people have needed to solve these, so they don't use backslash, they don't use the dense linear solve. Well, I'll go over that in a second. But instead what you do is you come up with better ways to be able to solve specifically the types of linear subsystems that you're going to be solving from these PDE operators. And that's how you do this well. So solving PDEs, right, once we've discretized it, really what it becomes is equation solving with large numbers of equations, but with a very high, high sparsity and a very specific structure. So how do you solve a large sparse linear system? So, well, the first thing is, what if it's tridiagonal, right? What if it's that 1 minus 2, 1 matrix where you have everything on the diagonal or one of the off diagonals? There's a special algorithm that will be able to do that in O of n, right? It basically is just able to loop down and it loops right back up. And so that's actually built right into Julia's backslash, so yay. But if you wanted to, you can say that, the capital T tridiagonal of my matrix tells Julia that it's tridiagonal, and it tells it do the tridiagonal solve on this matrix. If it's small enough, if your matrix is small enough, then using backslash can still make sense because it's a multi-threaded LU or QR factorization. But that's not going to make sense once you start getting to larger and larger matrices. And there's some other tools that you can use as well. So let's say you have not just a tridiagonal matrix, but let's say you have 5. So when I say a matrix is banded, what I mean is that it doesn't. you have these diagonals, and you have like the first diagonal, you have the next diagonal, the next diagonal. If you have a bunch of diagonals in there, that's called a banded matrix. And you can always change your matrix into a banded matrix, and if you call this backslash, then banded matrices.jl uses a specific type of linear solve for a banded matrix, such that I think it actually comes out as O of n, but I might get corrected in a bit. If you have a block banded matrix, so remember when I talked about these higher dimensional discretizations, what you do is you go by the x, and then you do the next in the x, the next in the x. Well, then going down the y direction is actually going to be very close to the x above it. And so that actually gives you this very nice structure that you have these blocks, these squares in your matrix that kind of get repeated, because you have the structure of things going across, which is right next to each other, and you have these things going down, which are n apart from each other. So that gives you these nice squares that repeat themselves in these matrices. And so you have these special, you have another package, block banded matrices, which can take it just adds a type to your banded matrix, and then it puts a special linear solver on that to be able to specialize there. So basically the idea is that you get these specific sparsity structures from your PDEs, and then there are a lot of people building packages for specifically solving those sparse linear systems which come out of those very specific PDE discretizations that people tend to use. And so you can keep on going. If you just have if you have a small enough sparse matrix, then you can just use backslash once again, because what Julie is actually doing in the background there is it's using a sparse LU. So it's using something called super LUMT. So it's a multi-threaded sparse LU, and it's able to work in that case. But once your matrix starts getting large enough, you don't want to you can't really make use of that, and so you need to start using something called an iterative solver. And there are two packages for it there. There's iterativsolvers.jl, and there's the much newer Julia Smooth Optimizers Krylov.jl. So this one is in Julia Math, this one's in Julia Smooth Optimizers, and they're really doing the same kinds of algorithms. And this is really what people, when you think about how do you solve the linear system that comes out of a PDE, these are the methods people are usually talking about. So let's go into a little bit more detail on those. All right, so just to recap, basically all these are saying if you know something very special about your matrix, right, if it's going to have a very special structure, then you can tell Julia through the type system, this is the special structure, where this is defined in some package, and then when you use backslash on that, it'll automatically specialize your linear solve to be able to make use of the structure that you said it has. But if you don't know if you have structure, and you just have a large giant matrix, a large giant sparse matrix, then you want to use an iterative solver. And what does that look like? So an iterative solver, it doesn't actually have to use the memory of your array at all. Right, so if you think about using Gaussian elimination, you go to your matrix and you say, take this row, subtract this other row, change my matrix. Well, an iterative solver isn't really doing that. And what an iterative solver does is you basically say, this thing does A times U, and it's able to keep on doing A times U. And if I add together A times U in a very specific way, maybe I will find the U such that A times U equals B. Right? And so an iterative solver actually only uses multiplication. So they basically put together the multiplications in a way so they converge to the value it's supposed to be equaling in the end. And the nice thing is that I talked about these matrix-free operators. Right? I said, there are these operators that aren't really matrices, but they have multiplication defined on them. An iterative solver can use this without ever making it into a matrix, because all it ever has to use is multiplication in order to solve that linear system. So iterative solver has quite a few methods, and once again, a lot of these methods are specific to the kinds of matrices that you tend to see in these PDE problems. So one of these is CG, which you might know of as conjugate gradient. So if your matrix satisfies something called symmetric positive definite, then you can use CG, and it's a fast one. And you could go through the package, and it says, for these types of matrices, you can use this one. It has it all listed out. But in the end, you can always use GMRes, so I'm going to show that. So let's show GMRes solving AU equals B, a linear system. It's really, there's not much to see, because all that you do is you say so let's build a matrix which is 10 by 10. Let's say that B is a vector of 10 values. Then using iterative solvers, what this is written as is A. So what you're trying to solve is A times U equals B, and I say that I want to solve it to a tolerance of at least 1e minus 8, and what it spits out is the u that solves that, right? So you want to solve the system a times u equals b. That is the same as a backslash b. So you put in the a, you put in the b, and it spits out what that u is. And here I'm just testing what is the norm of a times u minus b. It is something that's essentially 0. So it actually converged better than what I told it to do. And so an iterative solver is just a different thing than doing backslash. But this doesn't actually have to do a factorization, which, if your matrix is large enough, is a better way to handle it. And you can also, the other thing is that you can use a matrix-free type in here, right? So I said that it only uses multiplication. And so if you know how to represent your derivative in terms of only what your derivative function would do to a vector, then you can use this inside of iterative solvers. So let's do our Poisson example again, right? If you remember all the way back, now it was a bit of time ago. It was the u sub I minus 1 minus 2u sub I plus u sub I plus 1, right? That is a representation of the second derivative. So what we can do is we can say, here's my type. It's a size Strang matrix. This thing is called a Strang matrix. I give it a few overloads. I say its L type is a float 64. I hold what the size is inside of there, and I use these two definitions of size. And here I say that I want to create a Strang matrix which is the same size. It's a length of b by length of b matrix because I want to be able to solve a times u equals b. And now, what is my multiplication? Well, I don't actually have a real multiplication of my matrix. What I actually do is I actually write in there that loop, that b of I minus 1, so a times b equals c. What I do is I have the b of I minus 1 minus 2b of I plus b of I plus 1. And so if I do a multiplication, this thing will act like it was the matrix, which was minus 2's on the diagonal and 1's on the off diagonal. But there actually is no matrix here. It's just a definition of what a multiplication would be if this thing existed. And since I said that that's all that GMRes needs, I can put this type, this size Strang matrix, into GMRes as the matrix. I give b the vector that I want to solve, and then I'm able to solve a times u equals b just by using this GMRes. So this is really nice, right? You can get these gigantic PDEs where the thing that would really take up memory is the matrix, and then your matrix is actually represented in a few kilobytes or whatever that type is, because you don't actually have to represent it. So these iterative solvers can do these matrix-free methods where you just define what a multiplication will look like, and you can do a very large sparse solve. And this is actually really highlighting something about Julia, right? Where a lot of the packages, if you're using something like Python or MATLAB, they would want a matrix in order to do this. But in Julia, someone wrote it such that it just uses multiply, and so you can stick any type you want in there that has multiply defined. It doesn't matter that you defined it. It doesn't matter that it wasn't really a matrix. It just uses it anyways, and it will do it efficiently because it's using the, here's the non-allocating matrix multiplication. So it's really cool that, you can just stick any type in there that you need. You can create your own PDE, which has your own discretization. If you make this function and throw it in there, there was nothing special about this example. It'll just work on your type. So I just want to throw another plug out there. There's this linear maps.jl, which is a nice way to, so this was all done by hand just by using a type. Linear maps.jl lets you say, here's my function, which is a linear map of this input to this output, and it builds that lazy representation if you know it in its functional form instead of in its matrix form. So a lot of these Julia tools are really helping you be able to be more efficient with your memory and be more efficient with your computation by representing your functions in terms of a more, in terms of something that's using the dispatch mechanism. So one last thing is preconditioning. So you could use GMRes, but generally using GMRes by itself isn't that good. It converges somewhat slow if your matrix has bad properties. I don't want to go into the whole mathematics of that, but there are some matrices where you put into GMRes and it'll take quite a while because it needs to do a whole bunch of these matrix multiplies to finally get to the final solution. And so what people have come up with is you can, instead of straight using GMRes, what you can do is you can say, well, if I had a smaller problem, what would the inverse have been in that smaller problem, and exactly solve the smaller problem. That's pretty much what preconditioning is doing. So what preconditioning is you can say, I want to solve AU equals B, but there's a slightly simpler problem where this other thing is kind of like A, and I know how to solve that. And when you put those two problems together, then you are able to use GMRes faster. So you might go, well, that's a highly mathematical problem. How do you actually make use of that? Well, people have already made these packages for using a preconditioner, so you might as well use them in these cases. So for example, I said that the LU decomposition is one way to be able to solve a linear system. The incomplete LU is a almost inverse. So if you say you can use ILU.jl to be able to define, basically it just gives you a function where what it spits out is this object that does the ILU preconditioning. And you just tell GMRes, like, oh, add this preconditioner to my call. There's not much on your end to actually do. You have this other package, incomplete selected inversion, and then another one which is much newer, this algebraic multigrid. All that you basically do is you take this package, you add another keyword argument, and it adds a preconditioner on it. So, if you know what a preconditioner is, those are three nice ways to easily get preconditioners for three very common preconditioners. If you don't know what a preconditioner is, these are three packages that give you something where you put it into a keyword argument and it makes everything faster. You can spend an entire lifetime finding out how to do fast preconditioners, so there's no reason to go into more detail, but this is something that you might want to look into if you're using GMRes and your linear solve is not working fast enough. So another thing to look at is these linear solver parallelism libraries. Right, so there's actually going to be a few other talks at JuliaCon talking about at least this Trolinos library. So what does it do? Well, you have this giant matrix, and as you get to bigger and bigger PDEs, you have a more giant sparse matrix. And what these packages do is they give you a nice way to be able to represent a large sparse matrix on multiple computers, so multiple threads or multiple cores on multiple nodes on a cluster. And then you can say, let's do backslash on this gigantic matrix, and it has dispatches already defined, such that it knows how to do a sparse solve on that. So that way you don't have to write the whole parallelism yourself. This only makes sense if you have a gigantic PDE that you're discretizing, or if one way to get a gigantic PDE is you take a really small delta x, right? That's the same kind of difference. But yeah, so basically this is just another set of libraries where now they're using somewhat the similar methods. They're either using sparse factorization methods or they're using these iterative solvers, except on these matrices which are now defined using a special matrix type which is parallelized across a cluster, and then their own dispatches for the linear solve are using a parallel algorithm over their distributed matrix. So what this 3.1 portion is just how do you solve that matrix? How do you do linear solves that come out of that? So if it's sparse enough, you can just throw backslash on it and not care, right? If it's large enough, then you start needing to use things like Krylov methods, and then you start needing to use preconditioned Krylov methods to be able to speed it up. And then if you get really large enough, then you really need to use these parallelism libraries. And so there's no reason to really create the parallel matrices yourself because people have spent a lot of time in this, so you might as well use one of these three libraries to parallelize your linear solve and just call backslash on it. And then the other thing to mention is that if you have a very special matrix type, then you can use banded matrices.jl or block banded matrices.jl, and it will use a special linear solve on specifically the matrices that you are getting from your PDEs, and it will solve it faster. So really, the idea that I want you to get out of this is that these packages are your friends. All you need to do is you need to find out, what does my matrix look like? Is there a package out there that I can exploit on my sparsity structure? If not, then I need to either go big in parallel or I need to just go to iterative solvers. And so yeah, that's just how you solve the linear systems. But what I want to do now is I want to tell you about solving nonlinear systems. And what I want to show you is that it's actually the same thing as solving a linear system. So there are a few packages to use in this case. There is nlsolve.jl, there's sundials.jl, and there's minpack.jl. This should say sundials.jl. So kinsol is the function inside of sundials.jl, which is able to do the nonlinear solving. And so I'm going to say that the Kinsolve method inside of sundials.jl is the one that's recommended for PDEs now, but NLSolve is adding the right feature to be able to be useful for this. So what does Kinsolve have that the other ones don't that make it useful for PDEs? And the reason is, well, let's do one quick note before so let's leave that one as a secret for now. Let me just say, don't use an optimization routine to solve a root finding problem. So this problem actually comes up in the DiffyQ channel quite a bit. Someone says, oh, I need to solve that, this PDE discretization equals 0. Right? So this g of x equals 0. This is the problem I need to solve. Well, one way to be able to do that is you take the absolute value of g, and what's the minimum of the absolute value of g? Well, that's got to be something, well, if it can equal 0, then it will be 0. Right? So it's actually just an optimization problem on the absolute value to get the 0. Don't do this. Just don't do this. The main reason why is because an optimization so these optimization methods, what they're actually doing is they go, well, where is the optima of a function? It's where the derivative equals 0. So they're running a root finding algorithm on the derivative. And so, if you think about it, what this thing is actually doing is you say the absolute value of my g. If I want to do the optimization problem to find its minimum, the Newton method in that sense is using the second derivative to get to the 0 of the derivative to be able to recover what the 0 would be. It's a very indirect way of doing that. So just don't use an optimization. You can't. Basically, you can use, JMP is a really cool library. You can use it here, but it's just not the right thing to use, right? So what is a root finding method? What does it actually look like if you're not using an optimization library? What it is so Newton's method is just that the next iterate, so z sub, I actually wrote this incorrectly. This should actually be a dz. So the change in your z is your current z minus the inverse of your Jacobian times your nonlinear function evaluated at your current point. So what this j is this Jacobian matrix, which is the first derivatives along each direction. So another way to think about it is, well, to solve this equation, what you're doing is you're solving a linear system, right? This is where it comes in, where it's I wrote this down wrong, sorry. This is the Jacobian of the g function at the current point equals how you would change your z, or times how you change your z, equals the nonlinear function, right? So you just bring this Jacobian over. This should be a j. So every single step of Newton's method is you create a matrix, which is the Jacobian of your nonlinear function, and then you do a linear solve with that Jacobian. So the Jacobian, though, is just a matrix of derivatives, and what comes out is really, it has the same structure as all of your PDE derivative terms. So if you actually look at this, where this is actually written correctly and this is a j over here, then this j, really what it is it has exactly that same structure as that linear equation that you would have solved. And so you'd want to use exactly the same linear solve techniques on that. So when I said, well, what package do you use to solve the linear system? Well, you need to specialize it based on whether it's a block-banded matrix or use an iterative solver with a Krylov method and use a preconditioner and all that. Well, this is inside of the nonlinear solve. What you're doing is you're just repeatedly solving one of those linear solves until you converge to some solution. So in order to solve this effectively, you need to be able to solve this linear system in the middle. And able to solve that linear system in the middle, you're going to want all those controls that I told you about in that other part, where you can choose what packages you apply to be able to do all this sparse solving. So the thing that really makes Kinsolve good here is that it lets you choose exactly how you do that linear solve. And what NLSolve is missing is it doesn't have a way for you to be able to say what that linear solve is. It has it hard-coded in there to use /. But I know that Patrick actually has the PR already open to be able to swap out what the linear solve is in the middle there. And so then you'll be able to use all of your Julia tools to be able to say, Jacobian times dz equals b. How do you do that lin solve? Stick this other way in there. Because really, solving a nonlinear equation is just repeat. All of the time is spent doing this linear solve problem. So part 3.2 recap is really just that solving nonlinear systems is usually using Newton's method, And Newton's method is really just solving a bunch of linear systems. And so once again, you've gone back to the same problem that we had in the first place, that we want to solve a large sparse linear system, and all those packages to be able to accelerate that linear solving process are now what you want to use, but inside of a nonlinear solver. And so you want to use some kind of package like sundials.jl, which allows you to be able to choose exactly how you do that linear solve in there. And then there's other packages which are coming along, which are pure Julia, that will soon allow you to do the same linear solve swapping out. Because really, that's the part that you need to take control of if you want to make this efficient. So the last thing I want to go over is ODE solvers. And now it was a while back, so let me kind of go back a little bit. When we did the heat equation, or when we did the semi-linear heat problem, when we discretized it, we only discretized the x part, and so what we got was an ODE out, right? So we said that, oh, this was the second derivative plus a nonlinear function. Let's only discretize by changing the second derivative to this matrix, and now what we got out was an ODE. Now this ODE actually has some properties, like, you know, when we were at the linear solving portion, what I said is, oh, there's the same pretty much every PDE has the same properties. It has a large sparse matrix in there. Now this is an ODE with a large sparse matrix in there. So you probably want to use an ODE solver which is able to exploit the fact that that's a large sparse matrix. Right? The PDEs basically is the study of how do you get a large sparse matrix and how do you use a large sparse matrix. If that's the only thing you get out of this talk, then you will have gotten a lot. Okay, so we have an ODE where we now have a term with a large sparse matrix and maybe some other nonlinear stuff. What do you do there? Well, let's see. So features of a PDE-derived ODE, this is actually what I was talking about. So you have this large sparse Jacobian, right? So once again, you want to think about your nonlinear functions in terms of what their derivative is, the derivative between the different points. And just so happens that the Jacobian of your nonlinear function is going to have the same structure as your large sparse matrices. And the reason for that is these nonlinear functions, they only act at a given point, right? So if you have a nonlinearity here in space, that only affects its current point. So this really gives you a derivative term which is diagonal. You add this diagonal term to something that has a large sparsity structure. What you get out is that large sparsity structure. And so it has a large sparse Jacobian, and then this ODE is something which is known as stiff. So if you've seen the talks on differential equations at jail, stiff ODEs are something that require, what's the word, more difficult ODE solvers. So you need to use a specialized ODE solver for stiff equations, and you want it to be able to handle large sparse Jacobians. So what methods are applicable in this case? So one thing that I do want to just quickly get out of the way is some people say, well, if I discretize in space by second order, right? So if my error in space is a specific amount, then should I make it so that way my error in time matches that amount? And the answer is no, not at all. So the reason is because what you want to do at this point is say, now I have an ODE. How do I solve that ODE as fast as possible? It doesn't matter how much error I have in the spatial dimension. If I use a higher order integrator for the time dimension, I can just take bigger steps if I want to. Right? So the way to think about these ODE methods is you don't think about it as higher order gives you less error. That's not actually true. Higher order means it can take larger time steps. Whether larger time steps makes more sense on your problem it's dependent on how little error you actually want to get. So you shouldn't limit the ODE solvers that you're looking at dependent on how you discretize in space in terms of the order. The order is really just something that tells you, higher order methods are used for when you want less. Higher order methods are more efficient when you want lower errors, and lower order methods are more efficient when you are okay with higher tolerances. But you basically just go in there and you benchmark and you see which one's fastest. It's really hard to know in advance which one will do well. So what are the methods that you can actually use to solve a PDE-derived ODE? The basic way that you do that, the way that most people would say in most talks, is you would use an implicit method or a Rosenbach ODE integrator. So what do? They take your ODE, and in order to solve your ODE, they solve a linear system every single step, which is I minus gamma times your Jacobian of your ODE function equals b. So this is just layering it on, right? So I said this Jacobian has the same sparsity, has the same structure as the sparsity structure of your PDE. This I is the identity matrix. So now what you're doing to be able to solve this ODE is you're solving a linear system which just happens to have exactly the same properties as your PDE. And so what I want to point out here is that, in order to solve this well, then we need to do the same exact things that we did before. We have to say, well, in order to solve this ODE, we need to use the linear solver, which matches our PDE structure well. We need to put that in there, and then the ODE solver needs to solve this linear system over and over and over. It's basically, if you get only two things out of this talk, it's that every single way of solving a PDE boils down to solving the same linear system. And so if you could solve that linear system well, then you're helping out everybody in the PDE ecosystem, even if they're solving an ODE or a nonlinear system, because ODEs and nonlinear systems really just boil down to solving a linear system. So it's all the same problem. So what are the good choices for doing this kind of implicit method for solving an ODE inside of differentialequations.jl? There are three methods I would probably point at, and it's this CVODE BDF, KenCarp4, and RODOS5. These are the ones I'd point to that are in this class. So what's an example? Let's look at spectral time stepping for that heat equation. So let's discretize the heat equation in Fourier space and then solve it using CVODE BDF. Now we're putting together something that happened earlier in this talk, right? So we say that the space is Fourier. This is exactly how I discretized a function earlier in this talk. And then this is this right here, this D2, is exactly how I got that derivative before. But now I'm just going to turn it into a real matrix by indexing. So I can take my function, I can turn it into something that's in Fourier space. I can write my derivative in Fourier space. And then I can write my ODE as this as this problem in Fourier space, right? So in Fourier space, what it is it's just the matrix times the vector. And remember the A mul B, this is the old 0.6 way, which is going away, of saying L times U equals du. And so this is what the PDE is, or this is what the PDE looks like as an ODE. It's just doing L times U is the derivative repeatedly. And so I say this is my ODE. My ODE is that function, which is just the second derivative times my current values. And now solve this using CVODE BDF. Now why is CVODE BDF something that's useful here? Because you can specialize exactly what the linear solver is, right? If we went back a bunch of slides again, we're building on ourselves, and we're saying that, remember that this derivative in Fourier space was actually a diagonal matrix. So you can go in here and you can say CVODE BDF, use the linear solver, which is specifically for diagonal matrices, to speed up your internal solving, and solve it to a relative tolerance of 1e minus 8 and absolute tolerance of 1e minus 8. So what we've basically done here is we start with a continuous problem. We discretize it to a vector by using this transform, and we get the matrix out for our derivative by using the derivative function from approxfun. And now we say, oh, this is a way of representing our PDE as an ODE in Fourier space. We solve this ODE, and then to be able to get our solution out, what we do is we take our solution from Fourier space and we apply the inverse transform of it to get back to point space, and then we can plot those points. And what you see is that we started with cosine of x minus 0.1. So we start with this value right here, and over time, since this is the heat equation, it's diffusing. And so this is at time 0, this is at time 0.5, and then by time 2, we're almost at a line, and by time 10, all of our heat is diffused, and now we're just, we're the straight line of zero heat everywhere, well, a constant heat everywhere. So let's do something that now has a nonlinearity in it. So let's do spectral time stepping, where we now do this heat equation, U sub t equals U sub xx, and we also add a linear part. You can also, or a nonlinear part. You can also handle these equations with nonlinearities you do it the most simple way possible. You say that I know how to apply f to my function, but I don't know how to apply it in Fourier space. So if I want to solve my ODE in Fourier space, then if this u is hanging out in Fourier space, or if I want to solve my ODE in Fourier space, what I do is every time I want to apply my nonlinear function, I change it back to point space by doing this inverse transform. I apply f, and I bring it back to Fourier space. So remember that now this is something that you can do easily because a prox_fun tells you how you transform back and forth. So you just say, here's my, I'm solving everything in Fourier space, do the inverse transform, call f on that, do the transform back. And then what is this a? This a is that derivative in Fourier space. And that tells me how Fourier of u changes over time. So yeah, so basically what I'm trying to get at is that you can build these more complex methods for more complex ODEs, but it's using the same way that you would have discretized that PDE. So you use these, you either use the finite element packages, you use the finite difference packages, or you use the spectral packages like a prox_fun. All of these different packages give you a different way to write down this discretization. You get an ODE, and if you ever need to deal with nonlinearities, you just transform back and forth as needed. And you can write down this ODE as something that you can solve. You throw it to differential equations.jl. And now you're mixing a bunch of different packages, right? Now you're mixing a linear solver package with a discretization package, with an ODE solver package just to solve this PDE. And that's really why, this takes a whole ecosystem. It takes a village to solve a PDE. Now what I want to do as we're getting near the ends here, I want to go over what are the new kind of special methods that we have in differential equations.jl, which are specifically for PDEs, right? And so one of these methods is called an implicit explicit integrator, so an IMEX integrator. And what it does is instead of looking at your PDE as a single function, it splits it up into two functions, where you have this first part and the second part. And remember that you need to do a linear solve on the implicit part, and you need to have an implicit part if your ODE is stiff. Well, if only part of your ODE is stiff, it doesn't make sense to do the linear solve on everything. Instead, you can have part of it just be not part of the linear solve. And that's really what an implicit explicit integrator is it's just saying that I want to be implicit over here, I want to be explicit over here, and that will hopefully decrease the amount of work I have to do. So basically what the previous method over here was, let me just kind of jump back, where I said that you had to do this linear solve. This is where j is the entire function, this entire f. But if we split it up, now we only have to solve a linear system where this j is only part of f. And hopefully if you split it up correctly, you'll be able to take large enough time steps, but you will have also made your computation cheaper. So there are a bunch of different methods for this. So these are all brand new from one of our latest GSOC projects. So the Crank-Nicolson AB2 method, the SBDF2 method, the KenCarp3 and KenCarp4, these are all the different integrators where you tell it which part you want to be implicit on, which part you want to be explicit on. And usually you need to be implicit on the part that has the PDE operator. But the nice thing is that if you only have the PDE operator here, then the Jacobian is just that matrix. And so then you can write one of your nice little, you can write one of those matrix-free functions that will do the matrix multiplication without having the matrix, because that linear system you will know exactly what it is because it's only the matrix that you know how to write down. So these implicit explicit integrators are very nice for solving these problems where you have one PDE operator and then you have a bunch of other nonlinear stuff and you're allowed to split them up. So here's an example of that. So take the previous derivative that I've written down. Just assume that you remember that first part. Now, so this first part I'm going to say is that a times u. The second part is some nonlinear part. Did I write down the nonlinear part? I guess I didn't. So let's just say we're now solving the heat equation plus 0.75 times the square root of u minus u. And what we do is we'd say for the nonlinear part, the way that you solve it is you take your current u, which is in Fourier space, you inverse transform it back to real space or point space, which I put into this TMP here. You apply your nonlinear function, and then you transform it back to Fourier space. So now my ODE is going to be a times u plus this nonlinear thing. And so what I do is I define the split ODE problem, which has the matrix, which was that the PDE operator matrix. And then I have the f. I keep this nonlinear part separate. And then the ODE solver is able to use those two pieces separately. And so then I say solve this with KenCarp4. And this is one of those methods that's able to use the two parts separately. And then when I solve the ODE, you get this thing now, which incorporates this nonlinear term into the heat equation solve, or yeah, as the semi-linear heat equation. So these methods are quite nice, and the only thing they have to do in order to use them differently is you pass in two functions, or one operator and one function in order to make this work. So another thing that came from a recent GSOC project is exponential integrators. So the nice thing about an ODE with a linear ODE is you know that the answer to a linear ODE is just a matrix exponential. So if you can split it apart such that you have a linear part and a nonlinear part, what these exponential integrators are able to do is they're able to use this exponential of something times your PDE matrix times a vector. They're able to use a bunch of those multiplies to be able to solve your ODE really quickly. And so one example of that is this ETDRK4 method, which only works if you say that this first part is a linear, this second part is nonlinear. And the way that you said it was linear is just by passing it this operator, this diffeq linear operator. Then what it'll do is it'll apply one of these exponential methods, which will it'll exactly solve the linear part, and then it'll approximate the nonlinear part using Runge-Kutta order 4. And when it puts the two together, you get a pretty fast method for this. So this is something that you would have seen these types of ODE solvers buried inside of PDE packages, but now this is the kind of thing, if you dig inside of the differential equations.jl documentation for things that solve a split ODE problem, you'll find exactly these IMX integrators and these exponential integrators, which are specifically for these types of PDE discretizations. So note that there's actually a bunch of additional methods that you can explore, right? I've very, very, very much condensed the whole field of PDEs to say, oh, there's only 3 ways to solve this. No, there's actually a bunch of other ways to solve it. So there's other things that we're working on is these Runge-Kutta-Chebyshev methods, which are actually explicit methods. They use a bunch, I can go into them in more detail, but they're just an explicit method which is still able to solve a stiff equation. And so for some PDEs, that's better. For other PDEs, it's worse. The thing that is nice about the differential equations.jl interface is that inside of all of these methods, I noted to you that you had to solve linear systems. If you want to solve it efficiently, well, you need to tell it exactly how to solve that linear system such that it's good for your PDE. And if you dig into the documentation, you'll find that there's a way to be able to pass linsolve, where you tell it, I want to use preconditioned GMRes with an algebraic multigrid or whatever very fancy linear solver you want. You can swap that into the integrator, and then the ODE integrator will use that linear solver, because once again, solving the linear system is really the part that takes all the time and really needs to be the part that's the most efficient. Right? So the choice of ODE integrator, what it really does is the choice of ODE integrator says how many times you need to calculate your derivative function and how many steps you need to take. Every step you take is a linear solve. So with changing the ODE method, a good ODE method really just is less linear solves. But you still need to solve that linear system a bunch of times. And then there's also these SSP methods, these strong stability preserving methods. I just want to do this so that way anyone who's watching this video is like, I do my hyperbolic PDEs. I need these SSP methods, which are these explicit methods which are able to do larger time steps, so less calculations on hyperbolic PDEs. We do have these hidden in there too. So this is just for you in the video. So as a recap, all these ODE methods are doing is they're being able to solve that ODE with less steps. But solving it with less steps still just means less linear solves, and in the middle that still means you need to make sure that linear solve is efficient. So taking on this workshop of saying I'm going to teach you how to solve a PDE is actually was kind of a challenge, because there's so many different PDEs, and every single PDE you need a different method of sorts, but really they fall under the same the same route, where what you're doing is you're getting linear systems and you're solving them. So why do you want to use Julia to be able to solve a PDE? And it's because we have this giant ecosystem for doing each of the step of the process, right? I said that in order to solve these linear systems well, you need to use an iterative solver. And iterativsolvers.jl is a great package which is able to not just use matrices and sparse matrices, but it can use any abstract, anything that can do multiply. So if your matrix is defined on the GPU, if your matrix is defined by a type, it doesn't matter. You have a GMRes that's already defined for you inside of iterativsolvers.jl. And then, what if you have all these different structures? Well, people like Sheehan-Over have already gone through and said, if I have banded matrices or if I have block-banded matrices, I can specialize and I can get really fast solves on exactly those types of problems. So Julia has a very nice ecosystem of special matrix types for making your linear solves really fast on these matrices which you encounter with PDEs. Another thing is that you have tools like Kinsol and soon NLSolve, which they solve nonlinear systems, but they allow you to put in whatever linear solver you want, right? And since the linear solve is really the part that takes all of the effort, you're really putting in the most optimized code directly into the nonlinear solver and changing it so that way now it's optimized for your PDE. So that's a really nice feature of these. And then differential equations just has a bunch of other methods to be able to solve these ODEs, which once again what they're doing is they're making it so that way you have to do as few linear solves as possible, and they once again allow you to say how you want to solve that linear system by plugging in the linear solver. So, I mean, it's really building up. And what you have is these abstractions where you want to say the ODE system is really just solving a bunch of nonlinear systems, which is solving a bunch of linear systems, and I want to be able to stick a type in there such that I dispatch in a nice way such that I solve those linear systems effectively. And what Julia gives you is these zero-cost abstractions, such that at the very top you can say, here's my ODE solver, which has a nonlinear solver, which has a linear solver. You, the user, can change exactly how that linear solver is and change everything in that whole system to be well optimized for your PDE. And so I kind of went over that part fast, but just go dig through the docs and you'll see exactly, what you're looking for is linsolve, right? It's usually typed out LINSOLVE, and that is usually going to be the keyword argument that says, how do you solve this linear system in there? And when you pass that in, you will now have taken over its linear solver interface, and that's really how you make all these fast on PDEs. And the nice thing about this is I did forget to mention that a lot of these allow you to use abstract matrices. And so if it can be an abstract matrix, then you can not just use a matrix that is a sparse matrix on the CPU. You can also use a sparse matrix which is distributed across multiple computers. You can use a sparse matrix which is on the GPU. And a lot of these packages will work just the same. And just by using the Julia's dispatch mechanism, as long as you just tell it how to solve that linear system appropriately. So the conclusion is, if it should have been pretty obvious by now, solving a PDE takes layers and layers of tools. But each of these tools, they fit together like a glove, right? So you have these discretization tools, which what they do is they take your idea of a continuous function and it changes it to a vector, and that vector is how does this function look in a specific basis. And the other thing that it gives you is it gives you these matrices, these linear operators, which is a new way to write down what your derivative is in terms of that way that you represented your function. So you can't just have the representation of the function, you also need the derivatives, and it just happens that those are always some form of a matrix. So once you use a package to be able to get the new representation of your function and the new representation of your derivative, you're either going to have a linear system, a nonlinear system, or an ODE. But that linear system, you have a bunch of packages to solve. I went through those. But the nonlinear system is really just solving a linear system. And the ODE is really just solving a nonlinear system, which is solving a linear system. And so these packages, they just layer on top of each other until everything is really just about choosing the right discretization package plus the right linear solver package and throwing that into either Kinsol and NLSolve or differential equations.jl if you get the ODE. And then everything works together nicely. And so what's going to happen in the near future, right? So that is a very, when I started this talk, I said that what I'm kind of doing is I'm recruiting contributors because this is a nice group of people who are Julia people. So maybe you're someone who just does machine learning and you're like, what's PDEs all about? Well, now you know that if you have a problem and you want to be able to solve matrix multiplications or linear solves faster, you're actually helping out all the PDE people, right? But at a higher level, like, these are all the tools that we're using to solve PDEs. And now someone at the very end says, well, I don't want to do all that work, right? I want you to do all that work in the back end. I want you to solve this PDE for me. That's where we're going next, right? So we could say, here's your discretization package, here's your linear solver package, here's your ODE package, use all of these together. What we want to be able to do in the near future is on PDEs which are very popular, right? This semilinear heat equation is something that shows up in mathematical biology a lot. We want to be able to say, Well, here is a reaction diffusion problem where you say, I want to solve this on a square. Give me a discretization package, right? So you put a type in there that says, use a proxfun, and here's my nonlinear part. And you just say, solve it, and we can solve it with a given method. So that's where we're going in the future. And the way that we're getting there is by building all these pieces up such that we can then piece them together, give us a nice optimized pipeline. But even though we don't have these functions here right now, you can still do that process yourself by using all of these discretization packages and these linear solver packages and these ODE solver packages. So we are now very close. I said that a lot of this happened in the last GSOC to be able to build out more of this differential, the ODE solvers for this. And also, a lot of these preconditioners, a lot of the linear solving portion of the Julia ecosystem also came from the last year's Google Summer of Code. So next year, Google Summer of Code, I'm planning on making sure we get some people to build this out, and hopefully people can solve PDEs without knowing any of the mathematics behind. But at this point right now, you still need to know at least a little bit about this whole, what is a PDE, how do you represent it as a function, and then you get a linear solve. So hopefully, if you're here right now and you go, I have my own PDE and I want to be able to solve it, this is how you put together the 15 packages of Julia's PDE ecosystem, and you get something where you can solve a giant PDE, and you go to your advisor and say, my paper's done now. All right, and so there's a lot of people to acknowledge here because I put as the acknowledgements everybody who has been contributed, or any of the big contributors to any of the packages that I mentioned. And so, you have some people, you have a lot of the GSOC students inside of the Diffie-Q organization. You have Sheena Over, who built a lot of the approxfun and banded matrices.jl. You have more Diffie-Q people. You have Bart, who worked on things like Truinos.jl, the large sparse matrices. You have more Diffie-Q people. You have people who built iterative solvers.jl and nonlinear nlsolve.jl. Right? All these different packages come together to be our PDE ecosystem. So as you go through the rest of your JuliaCon experience this week, you'll actually see a lot of these people give a talk. You'll hear some of them talk about how do you solve a linear system fast. You'll hear some of them talk about how do you solve a nonlinear system. You hear some of them talk about how you solve an ODE. And you'll hear some of them say, well, here's how you solve a PDE. And we're all talking about the same thing. We're all layering these same tools to be able to solve very similar things. And this is really what the PDE ecosystem is. It's not one package. It's not one person. It is a huge group of people who are all working together to build a system of tools which work together. So that was kind of a redundant way of saying it, but hopefully you understand PDEs a lot more now. So there's a microphone for questions. If anyone has any, I think it needs to get passed around because there's no way I could walk back, though. Yep.
Okay, so let me just express maybe a little skepticism and have you comment on, so for my problem domain, the idea of using the Julia ecosystem of packages to compose them together to solve PD, it seems like it's not really going to get to problems of where it is right now. It's not going to get to problems high performance computing of nonlinear PDEs. Like if you take all the pieces together, I feel like the composition's not going to cover like a big spectral fluids code, which is my problem domain. In particular, it's that the weakness seems to be the distributed computation. Like the only component applicable to the distributed computation was Coles-to-Trillinus and PETC and so on, but it doesn't seem like you have the Julia infrastructure for distributed computing as a component to this ecosystem so that you could combine all these packages without ultimately reverting. Because the only thing that those packages cover, as far as I understand it, is distributed matrices. And a lot of these algorithms for nonlinear PDEs, there's a lot more distributed computation going on than just the linear solve.
Yeah.
So, okay.
Yeah,
is that clear enough?
Yeah. So
comment?
what needs to happen in order to make that work well is basically you can't just take your ODE solver and say, oh, that same ODE solver, run it on the CPU, that solved that. what you need to be able to do is say, if my array is distributed, then when I do an element-wise operation on my distributed arrays, I need to do that operation as distributed as well. And that is actually where Julia's broadcast mechanism comes in, right? So Julia version 0.7 really solves this well, because if you go to Bart Jensen's talk, I think he's actually going to talk about his MPI arrays.jl, where what he has done is he's defined broadcasts such that broadcasted operations are done in a way that is distributed. So what I mentioned by broadcast, that is the dot operation, which is the element-wise operation. And so what we can do in Julia with one of the newest versions is you can easily say, I want element-wise operations to take place like this. So the element-wise operations are now defined by however the array type wants them to be defined. And that's how you can do GPU computing well. That's how you can do MPI arrays well if all that you're doing is broadcast. Right? And so what the actual way that the ODE solvers are made, so as you build up, the way that the ODE solvers, and hopefully we'll get NLSolve.jl to as well, is that internally they're only using broadcasted operations and they're doing linear solves. Which means that if you give it an array type which says broadcasted operations are all distributed, then the internals of that package, when it compiles on your array type, it will be all distributed. So basically, your array type takes control of the internal computations. And then the only part that isn't, that you didn't have to take control of, is that linear solve, right? Those are the two things that the package is actually doing. It's doing linear combinations broadcasted, and it's doing a linear solve. So if you tell both of those parts that it needs to be distributed, then everything about those packages' operations are distributed. And that's how we're getting there. So the broadcast overloads of 0.7 were a big feature in order to be able to do this. And then the other thing is being able to overload the linear solve internally. And so that's the part that we're missing in, say, NLSolve.jl. But when we have that, then there shouldn't be any serial operation if you apply it to an MPI array. It should all be able to be changed to be distributed. Now, the next thing is that we need really good distributed array types. And that's the part that's kind of been lagging behind. Because we need, MPI is definitely the best for building something that is distributed and low latency. And so distributed arrays just doesn't work well for that. But this other tool, MPI arrays, it's in the name. It's actually an array type which is built where it's distributed. You can tell exactly how to distribute the array. And then it's all of its computations, its communications are using MPI. And so that's really the key, right? So now we have an array type where when you give it to these packages which work on generic array types, what it will do is it will recompile the internals of that package so that it's using MPI for all of its internal operations. And then it's just up to the person who creates the array type now to make sure that those operations are fast. And then that takes the generic code and makes it, the fast code. So it's not as simple as saying, oh, I want to be able to solve this PDE and I want to use MPI. So here's my PDE code discretized with MPI. But instead what we're doing is we're using all these code generation tools and abstract array types such that we get there. But the ODE solver doesn't actually have to know about MPI in order to actually do all this. So it's a really cool way of getting there, I would say. But it does take a little bit more development work. But in the end, what we get out of it is it's not specialized to MPI. Those same functions will work on the GPU and other distributed ways as well. And I think that to get an answer that which really satisfies you, I think we're going to need a whole year of having 0.7 and 1.0. But this is the stuff that we're building towards.
As long as I can see the solution,
yeah.
what's in mind and working towards it.
There's also the transforms that also have to be distributed.
Yes.
So that's
Yes.
Yeah, the transforms have to be and that's the guy working on that. Oh yeah, and we also need the distributed fast Fourier transforms. Yeah. Any other? All right. Well then, thank you very much for coming, and welcome to JuliaCon.